Hey, good afternoon. How's your day going all? Can you hear me okay?
Yeah.
Okay, just want to check my mic, see which one I'm using because it's always bad when you're using the wrong one. It picks up way too much background noise. So if partway through class, I just did a microphone adjustment, hopefully you can still hear me okay. And then if I need to adjust over to the Bluetooth headset that I'm wearing for a mic, it's going to sound a little bit different, but it might be necessary. We'll see how it goes. Hopefully your day is going well. I feel strange in that this is like the class that I'm doing live this term. In my other class, I start with every day, good morning or good night or whatever it is. And I'm then thinking to myself, I don't even know what time the students are watching that video during. So this is at least good for me. Okay, so I sent y'all an email and I just want to mention a couple things administratively before we pick up with new material. One of the things I mentioned in the email is lab groups. There were two specific needs to change lab groups that students had mailed in, and that's fine, doesn't matter to me. And the reasons were, in my mind, pretty good. Okay. And so I figured I should toss it out there and see if any of the others of you had a desire to change or a desire to not change your group or whether you're willing. And I did shuffle a couple of you around, and I believe one student in the class, and I think it was Harrison, and I apologize for this in advance, Harrison. I couldn't quite get exactly what you said you preferred. And so I rolled the dice and said, Harrison, if someone has to take the fall today, it's you. And let me know if there's a problem with this. And now that I've said this, you're going to feel really embarrassed if you later tell me, oh, I don't like those people that I was assigned to do a group with. Um, so I'm just setting you up for like a bad situation there. Hopefully you don't mind. Um, but I did adjust some of the groups and I tried my best to make sure that the pre-assigned breakout rooms match up to the groups that you will be assigned to turn your lab reports in with. But one thing I've noticed with breakout rooms is even though I can attempt to pre-assign people to them, it doesn't always work perfectly. And if there's a little bit of a wrinkle, at least I've got two files up right in front of me here where if you don't pop into the room that I had assigned you into, um, then I know at least how to put you in the right one. And then again, right after I do sort of release you to work on the lab today, if you flag me and let me know, hold on, this is definitely wrong, the group that I'm in, we can adjust that. Okay. So I think we're good there. Second thing is, yeah, homework, you should have turned it in. And I think I put the answers online already. And if that's the case, great. You have the opportunity to turn in the homework and then look at the answers right away. And the grader has not indicated that she has started grading your homework sets yet. But my recommendation is you might want to look over the answers as soon as they're available and just think Monday afternoon sometime. Because if you turn it in on Monday and then wait until you get the homework answers back from the student grader, if that's like Thursday, you've missed a little bit of an opportunity to sort of check your answers right close to when you turn them in. Okay, so that's the second thing. Maybe administratively, that's all I'm remembering. Do any of you have administrative questions? Yeah, Anise says no. And you are the spokesperson for the whole class, of course. So anyone last call, or you let Anise speak for you? Or in this case, a muffled nodding of the head. Okay, so I'm good with that. How about subject matter questions? Did anything come up in homework or related to homework that you'd like to address, even though the deadline has already passed? Sometimes it's better to talk about things earlier than move on because I think I know this stuff, but if you don't feel 100% comfortable with any of the things that did come up, now's a great time to talk about them.
Can we go over the last question from the homework?
The trees and finding the sample size.
Just the very last one.
Okay, so let's see if I could find that. And I'm going to share a screen, and then maybe we'll look together at that homework assignment. So I think that was in week 1, so I could find that here under weekly content. Click. And week 1, review. And then, yeah, there was some homework problems. And at the bottom, there you go. What if you want a confidence interval to have a desired margin of error plus or minus 50? If it's a confidence interval for the difference of 2 population means, that's really the context that we're working in. So I'm going to sort of see if I could switch gears and then outline the whole thing from the box model to the conclusion on a separate piece of paper. And we'll see if you're happy with the answer there. And who asked the question? You, Chen?
Roxanne.
Okay, who? Okay, Roxanne. Yeah, thanks. Okay, so where is that? Okay, that should be here. Here we go. So I know my confidence interval procedure looks something like this. The confidence interval for the difference of 2 population means is y bar 1 minus y bar 2 plus or minus. And rather than writing this as t, I'm going to say plus or minus 2. And the reason I'm using plus or minus 2 is 95% confidence typically goes with a t value of 2. Okay. And we could talk about that another time. I'll just say if you were to use the t table exactly, you could get a slightly different answer, but it ends up being an iterative process. So I'm just going to say for now 2 conceptually times the root of s1 squared over n1 plus s2 squared over n2. So far, so good? You want that plus or minus part to equal some target margin of error that I'll term E. So I'm speaking generally, although the problem says, oh, 50. So if I were to try and solve for the sample sizes N1 and N2, that's 2 missing values and 1 equation. I think there might be an infinite number of possible answers. 1 equation, 2 unknowns, yeah, not so straightforward. So we'll do a little bit of algebra to solve for maybe N1 and N2 sort of, but still we'll find that we need to do a little bit of additional work. So E over 2 squared should be equal to S1 squared over N1 plus S2 squared over N2. Now, when I do algebra, I sort of skip sometimes a step or 3 because I just do it quickly in my head. And so because of that, I like to pause and say, okay, do we all get that? So E is on the left-hand side, divide by 2, square both sides. Okay, that works from my point of view. But anyone want to pause to talk about that so far? Okay, so I cannot find 2 separate unknowns, N1 and N2, even if I knew E, and I know 2, that's easy. And even if I knew S1 and S2, I cannot solve for N1 and N2 simultaneously. So approaches that you could take are, suppose N1 equals N2 equals some common sample size N equal to both separate groups. You're walking through the forest and you say, I need to find N male trees and N female trees. What is that N going to be? That is one approach that I could take. And if that were the approach I choose to take, I'd say 1 over n times s1 squared plus s2 squared should be equal to e over 2 squared. So I guess n, and let's put n over here on the right-hand side because that's easy. And on the left-hand side, I've got s1 squared plus s2 squared times then 2 over e squared. So that's one approach I could take. So you happy with that answer, Roxanne?
Yeah, that works for me.
Okay, so now I want to adjust it to make it an even better answer for some of you. And I'm going to pitch it this way. What if male trees were very few in number and female trees were quite large in number in the forest? You're telling me I'm going to have to find, say, 80 male trees and 80 female trees? That's going to take a long time wandering through the forest to find. Well, it's easy to find the 80 female trees because there's a lot of them, but the 80 male trees, that's going to take a lot of time, yeah? So what if we know the ratio of number of trees of the male variety and of the female variety? What if I tell you that for every male tree, and I'll call that NM, there's say a constant, and it could be 10 times NF. Okay, so if I tell you there's 10 female trees for every male tree, I guess I could then similarly solve for what I need to solve for. So I'm going to go ahead and, oh, don't want to clear the whole thing. I'm just going to erase some over here and see if I could then plug in appropriately and then point you the right direction. So if that's the case, I'd say, well, S for the males squared over N for the males plus S for the female trees squared over K times N for the males. Now I've got just that one value, and M, that I could solve for. So Roxanne, I think what I'm suggesting is this. If you have a default or base rate that you sort of know of, and I'm thinking with days of the week, you might have 2 weekend days for every 5 weekdays, Monday, Tuesday, Wednesday, Thursday, Friday, then Saturday, Sunday. Or if you have a ratio of, say, trucks to cars, you want to know how much more weight trucks have in them than cars do. If you're in highway management, you sort of like looking at how heavy these vehicles are, and you're just wanting to know how much more the trucks weighs than the cars do on average. And the ratio of trucks to cars coming down the roadway, you could say, well, let's get approximately NM, and I'll set NF to correspond to NM to be a constant, that ratio, if you will, the number of this per every one of that. Okay, so this is a general idea that you have. If you have two unknowns and only one equation, if you could relate those two unknowns to each other and say this one is sort of knowable based on that other value, you could solve in terms of the number of the one type of individual and then broaden out to get the number of each. So I think that's sort of a nicely fleshed out answer, especially in the context of these trees with about 60%, I think, female trees and 40% male trees. That is not necessarily the only answer that you could give, but that's sort of a nice touch that would be acceptable in my mind for this homework. Okay,
I have a follow-up question, if that's okay.
works for me.
How might one, so as a grad student collecting data, I'm pretty lazy and I don't want to count flowers on trees all day. How might I minimize the number of samples that I need to take in order to, the number of trees I need to count the flowers for?
Great question. So Have you taken stat 324?
No, I've only taken stat 350.
Okay, and then this also comes up with stat 421. Okay, so again, it's y bar 1 minus y bar 2 plus or minus. And I like the intro. Suppose I'm a lazy grad student. Like that's a
Couldn't be
thing.
me. Couldn't be me.
S1 squared over n1 plus S2 squared over n2. The way you would minimize the number of data points in total, okay, is going to be found based on, well, knowing S1 and also S2. Yeah.
So in the problem, the variance of the female trees was almost twice the variance of the male trees.
Yep.
So maybe let's say we had 100 for S1 and 200 for S2.
Well, okay, that's based on, okay, so okay, so you're with background in computer science, Morgan, right? Okay, and then a couple of, at least 2 others of you do have considerable computer science experience. But I'm going to say, could you plug in the S1 and the S2 that you know the value of, and try various N1, N2 pairs that perfectly match that target margin of error? Like if I tell you N1, could you then solve for the N2 that corresponds?
Oh yeah, if you give me one, then I can solve for the
And
other. But I want to
then
minimize
the claim-
N1. Oh, go ahead. Sorry.
And then what you could do is, what you could do is find the N2 such that N1 plus N2 is the smallest. That minimizes the number of trees. But minimizing the number of flowers that you count, that can't exactly be done. Because if you tried to minimize the number of flowers, you're sort of going to be trying to bias your sample. And that's not really the purpose of this. The purpose is to see how many more flowers the one sex of tree has than the other sex of tree.
Of course, that I mainly meant count the number of trees to count.
Yeah.
How to
And so-
minimize that number.
And that search algorithm, finding N2 as a function of N1, okay, it turns out to be corresponding to N1 over N2 should be proportional to S1 squared over S2 squared.
Oh, okay. So it's
Yeah.
proportional to the standard to the variance.
The variance. Yep.
Okay. Interesting. Okay,
So,
thank you.
and there is a full-on class where, actually 2 other classes where we do consider that question, but they're
Okay.
usually for stat majors at the upper division level.
So I would
okay.
imagine you take the derivative of the equation and then set it
Well,
equal to 0.
In that class, yeah. But I think in general, it's pretty easy to solve for N2 in terms of N1 for that target margin of error, and then search across all the possibilities to minimize the sum.
Okay. Thank you so much for answering my question.
Okay.
I had a
Another
question.
question?
What is the
Ali.
value of the E for the homework assignment? Is it 50 or 100?
Yeah, well, okay, so let's look carefully. I had meant 50, but let's make sure that that works. Okay, so plus or minus 50. Yeah. So 50
what,
is the margin of error, the plus or the minus. It has a width of 100, but you're going up and down each to 50.
so E is 50, right?
Correct.
So why in the solution that you have posted, you consider E as 100?
It probably was a typo, or maybe I changed the answer, the question, or the answer from one implementation of the class to the other.
Gotcha.
So I'll look at that and I'll maybe adjust that answer, because if the answer online is not right, that's really bad. I should correct that before the grader gets to it.
Gotcha.
So thank you
so
for
much.
mentioning that, Ali.
Sure.
Ali or Ali?
Ali,
Ali. Okay. I'll do my best.
thank you so much. I appreciate it.
Okay. Anyone else? Okay, so what I want to do then is remind you all, please interrupt me as we go through the material. If something pops into your mind and you're saying, well, but what about? Mention that right away, because if you do, it could be a better interactive experience. But, you know, to be honest, some of you pause and think slowly and then later come back around to your question, in which case, the beginning of class the next time is a great time for raising those issues. ANOVA, analysis of variance. As I suggested in the Canvas, ANOVA is when you want to compare the group means across more than just two groups. It will work if you have exactly two groups. But if you definitely want to compare across a 3 or more groups, you need to use the analysis of variance procedure rather than a t-test. And we should be explaining in class today the why, and then diving into the logic behind the method. And then after we've defined or described the logic behind the method, you'll be working away at the lab today. Now, I do have to say the logic behind the method usually takes students, even at the 513 level, about 2 or sometimes 3 class sessions to sort of fully come to terms with. Some students are a little bit more quick with thinking quantitatively, and others are a little bit slower. And it's not based on intelligence, and it's not based on even your skills and abilities with math. It seems to be something that's inherent and unpredictable across students. Some people who have horrible math grades just click with statistics, and others who have been quite good at calculus and everything find certain statistical concepts challenging. I asked a faculty member at Stanford once in statistics, hey, who are the best grad students in your program and who are the worst? And his answer was, our best grad students who are people who are in the PhD math program at Stanford and then switched over into stats after 1 year. And the worst are people who were in the PhD program in math for 2 years or more before they switched over into statistics. There's something about math and statistics where literally the one doesn't help the other. Although we use a lot of the concepts mathematically, we think a lot more like engineers many days. You have to sort of live in the limbo between mathematics and engineering, reality, and then sort of thinking abstractly. And so I'll just say, if you got 2 groups that you're trying to compare, think t-test is the best. You could use an analysis of variance, but the situation when you have to use analysis of variance is if you want to compare multiple different groups of individuals. So the example I wanted to bring to you is one that I've shown you some data here for. We've got data, and it's right out of the Ramsey and Schaefer textbook. I've got data on the diet of some mice, okay, and literally how long those mice live. So I call it the diet and lifespan example. And if you're opening up data right in front of you, it's called diet and lifespan.jmp. I'm using JMP here primarily because I prefer it to Minitab. But we have different diets that we could give to the mice. One of the diets is called NP. We give them normal Purina rat chow or mice chow, and they eat whatever they want. They just big bowl and they eat as much as they want, and we keep refilling. Another one of the diets is called N/N85. They get a normal amount of food both before and after weaning, and normal means 85 grams or calories per gram of body weight. Now, I'm not sure whether that's calories or kilocalories or whatever. I'm just saying it's based on the metabolic rate of the mice, okay, and how heavy they are. And so you weigh the mouse and you give the mouse food that's deemed biologically optimal. There's a low protein diet that we could give to the mice. We could give a reduced calorie diet, 50 calories per day per gram of body weight. After weaning, we could reduce it to both before and after weaning. Okay, we could go with reduced to 40 calories. 85 is optimal. 40 is like less than half. So the different diets, low protein, N/N85, N/R40, reduced calories after weaning.
50 calories per day, NP, and then Bruce both before and after weaning, 6 different diets. And I guess what I could do is use a bunch of t-tests to see if all the means are the same. Because if I could compare diet 1 to diet 2, and diet 1 to 3, and 1 to 4, and 1 to 5, and then 2 to 3, 2 to 4, 2 to 5, 3 to 4, 3 to 5, and then 4 to 5. Oh no, 6 different diets. 1, 2, 3, 4, 5. 15 separate comparisons. I could do 15 t-tests. Would that be easy to do? I mean, could I just write computer code that just cranks through and does 15 separate t-tests? Not too hard. So to tackle the question, are all the means the same? I could use 15 separate t-tests. The drawback of that is the following though. Each of the t-tests that I do, supposing in fact there is no difference in the means, there's a 5% error rate, 5% chance, if you will, of thinking there's a difference in the two means when in fact there isn't. Type 1 error rate corresponds, and it's that past stat class, but I'm just saying if the null is true, if diet 3 and diet 5 are really the same, there's a 5% chance that the t-test that compares diet 3 to 5 ends up rejecting the null incorrectly. We might believe that diets 3 and 5 are different when in fact they're the same. And if I do 15 separate procedures, each of which has a 5% rate of error, you're thinking the error rate could be large. It won't be exactly 75%, but it will be very large. So 15 separate t-tests as a procedure is probably a bad idea. What we want to do is maybe do one overall procedure that limits the overall error rate to only 5%. The null hypothesis is all of the means, they are the same. Mu 1, 2, 3, 4, 5, 6, the 6 different diets, all the same population mean. Whatever the mouse eats, it does not impact the lifespan of the mouse. On the other hand, at least one of the groups is different. At least one of the diets is different in terms of the average. The average diet is either the same in all groups or at least one group is different. Okay, so I'm going to sort of jump past this test statistic for a moment, right to a p-value, and then we'll hit a conclusion, and then we'll go back and talk about the nature of the test statistic next. Inside JMP, to get to an answer, and this is sort of like what the lab instructions walk you through doing, either with JMP or Minitab if that's your preference. Under Analyze, fit Y by X, all you got to do is identify what's the response, well, how long they live. And, well, what does it maybe depend on? What you feed them. So does how long a mouse lives depend on what you feed it? That's the natural question I'm asking myself. And typically, when you fill in the blank spots in this construct your model statement, does lifetime depend on the treatment? The natural way of posing the question is the order that you'll fill in variables here. Does the lifetime depend on the thing you feed the mouse? Click OK. I see over here on the wrong screen, but I'll drag it over. I see a dot plot. And this is sort of like the dot plot that was shown to you earlier. Okay. I could, if I wanted to, turn on some features. You could spot here under display options. Yeah, show me box plots. If you want to see box plots, you got box plots. You could turn off and on various characteristics of the graph under these display options. I could show you averages for each of the different groups. Shown in green, average here, there. You know, the different group averages are shown here. But if I turn on this procedure called ANOVA, by the way, comparing means, yeah, literally comparing means is not what we do as a procedure within the software to compare the means. We use analysis of variance to compare the means. Strange name, perhaps. I could talk to you in office hours about why that's the case if you'd like. I'm just going to turn it on and I see a bunch of output appearing. And I like to not adjust the defaults in JMP so it looks sort of like to you all what you would see appearing in front of your screen. And I just get in the habit of turning off things that don't matter to me. For right now, I'm just going to go ahead and turn that off, and I'm going to turn this off. And I'm going to focus in on this thing here called the p-value. P-value less than 0.0001. My choice is either believe the null hypothesis, and we saw something that was so freakishly unlikely it would happen in less than 1 out of every 10,000 experiments, or I believe that at least one of the diets is better or worse for mice. I'm thinking it's easy to reject the null, believe the alternative hypothesis, yeah? The p-value small, believe the alternative. Okay, so what about that test statistic? We hit the p-value conclusion. The test statistic is always a way of quantifying how closely the data match up to the null hypothesis situation. The null hypothesis corresponds to all of the populations are exactly the same on average. So let me ask you, what do you think the data should look like in the samples if the population means are identical? Okay, I didn't mean that to be a rhetorical question.
They should all be on the same plane.
Yeah, exactly right, Ted. What we're seeing here is the separate sample mean shown here in green. Actually, these are mean diamonds shown. Maybe I should just turn off the mean diamonds. This way I'm showing this the mean diamonds. Just leaving the mean green lines in green. And maybe I'll turn off the box plots to get rid of the mess. Okay, so all of the individual group means here, all 6, they should all be quite close to that one common average constant height, the average lifespan of all the mice, yes? So the null hypothesis corresponds to all the group means are about the same. The data should be similar on average in each of the groups. The question here that I have is, are these data here far enough apart from each other that I'm convinced that the corresponding underlying population means are? So this is where I think probably. The reason I'm thinking that is, look at this group. Every single one of the mice eating this NP diet dies before the average death date of mice. And these NR40 mice seem to, well, shoot, at least 3/4 of them live longer than average. If 3/4 of one group is well above average and all of another group is well below average, at least this NR40 and that NP diet seem to be different from each other, yeah? Okay. So inside this analysis of variance table, you find literally our test statistic. It is deemed the F ratio. It is a way of measuring how far the data are apart from what they should equal if the null hypothesis is true. If the null hypothesis is true, on average, the F ratio will be about 1. If indeed the null hypothesis is false, the F ratio tends to be larger than 1. Now, here's where I'd like to use an analogy, and I hope you don't mind analogies because I'll use them all term long. Do y'all remember that physics class in high school where you had a fairly complex equation to solve, and so you filled one whole page of calculations, and then you wrote down an answer at the bottom, of that one page, and then another whole page of calculations and wrote down another answer, and a third whole page of calculations, then another answer. Then on the fourth page, you took the first three numbers and inserted them into yet another equation to ultimately get your answer. Y'all remember that sort of problem? Okay. The ANOVA table is exactly that. The guy that invented the method, R.A. Fisher, worked by candlelight at night at home to get his calculations done. It would take sometimes a week's worth of hand calculations to get the answers written out completely. So he got in the habit of summarizing the data in a convenient way for him to then be able to later go back and check the intermediate steps in case he had made a calculation error. That's the habit he came up with. And that's now what we call the ANOVA table. Another analogy is this. Remember Excel where you punch in one number, then all of a sudden all the other numbers in the whole table change? This is a table just like that. And in this ANOVA table, the input, okay, is essentially the means and the standard deviations and the sample sizes for each of the different groups. If I turn on this section that calls means, I can see averages, standard deviations. They're not shown to me here, but I guess I could turn on the means and standard deviations. Let's turn that one on, means and standard deviations over here. Downstairs, we get the means and standard deviations. If I tell you just the number of data points from each group, the average and the standard deviation for each group, this entire table could be done by hand. Typically in this class, we don't focus on how you could get from means and standard deviations and sample sizes to the ANOVA table, but we will over the course of now through Tuesday of next week, be sure to get you through seeing those equations at least once. Okay. Let's see what the next slide has for us. Okay, so in JMP, you're gonna just go ahead and do this. You find your conclusion from a p-value. The test statistic literally is how closely the means match up to each other in some general sense. And we will later, next class session, talk about the assumptions and requirements of the ANOVA procedure to even be reasonable. Let's dive in on our friend, the sum of squares between the treatment groups. You could see in the ANOVA table, there's a column called degrees of freedom. There's a column called sums of squares. The number here that we're defining with our equation is the sum of squares between the treatment groups. So in our case, here's 12,733.942. That's SST, the sum of squares between the treatment groups. Working from the inside out, we're going to compare individual group averages to some other number. Y bar bar. Y bar bar. What is that? It's not the average of the averages per se, but it's the average of all of the data values. We're going to compare individual group means to the average across all of the data. And if all of the population means are identical, then the group means should all be quite close to the average of all the data points. This interior value, before you square it, should be quite small if the null is true. Squaring a small number, it's still small. Even if you then multiply by n the number of data points per group, SST tends to be small when the null hypothesis is true. If, on the other hand, one of the diet groups causes, the mice to die young, and then other mice live a long time, you'd see, at least in those two groups, one of the groups with a group average that's far away from the average length of life. Like our friend over here. Shoot, what was the two I wanted to compare? Yeah, NP being one of them. NP here its group average is quite far away from the grand mean, the average of all the data points. So for NP, it's quite a bit below. This would be negative huge, where huge you get ginormous, and then multiply by n to even more bigify it. SST will be large from simply NP as a diet group on average being far away from the grand mean. Similarly, NR40 being the group that's well above average, Y bar for that group, high, compared to the grand mean, shown here, the vertical line or horizontal line. Large squared is big times the number of data points. Yes, SST will be large because in this case, the group means are far away from average. Okay, so that's a measure of how closely the data match the null hypothesis, yeah? Shouldn't we be done? Oh, okay, so that was not meant to be a rhetorical question either, but hell, we'll proceed as though it were. Yeah, no, we're not quite done yet. So, why aren't you done? Sometimes life gives you units that you're unfamiliar with. Now, if I were to tell you the radon levels in homes in the state of Minnesota in picocuries per liter, and say that the average radon level in Minnesota homes is 4.2 picocuries per liter of air, is that a number that should cause concern for the state of Minnesota's public health people from the point of view of, extra cancer because of the radon in the homes? Do any of you know picocuries per liter and whether that's dangerous or safe? I'm looking around the room here. Do any of you know picocuries per liter? Yeah, no, these are units that no one really finds natural unless you're in the area, yeah? My dad actually at one point in time he was a bit of a snotty high school student, and when he did physics in high school, he turned in his answers in some problems in foot-pounds per fortnight. He was always right when he turned in the answer, right? But the teacher got really pissed off because who answers in foot-pounds per fortnight? A fortnight is 2 weeks, by the way. But my dad did that, got the answer right, but the guy really resented my father for a reason. Okay, so unusual units, SST works in terms of unusual units. Unusual units, you need to convert them into natural units, yes? If I told you heights in metric, some of you think, oh, I speak metric, no problem. 165, is that short or tall for an adult male? Some of you would say, oh, a little bit shorter than average. Others, you would say, I don't know. I don't know metric from the point of view of inches and centimeters and stuff. But here, SST of 12,733, is that big? Well, that's my question. Is it large? I'll again argue via analogy. In our t-test, the numerator was the difference of the two sample means. How close are the sample means together? And we divided through by terms that related to spread, measures of spread in each group, and the number of data points from each group that we took. The measure of difference between means was compared to the sample sizes and the spread in each group. In that same sense here, in the ANOVA procedure, that F statistic, the F ratio, to use our book's terminology, I'm sorry, the software's terminology, it's that sum of squared treatment that we defined, divided through by things that relate to the spread within each group and the number of data points per group, and then also the total number of data points and the number of groups. The entirety of this ANOVA table here is converting this sum of squares between the treatment groups into another number F, which is large when the null is true, small, close to 1. I'm sorry, which is large when the null is false, and it tends to be about 1 when the null is true. Okay, so that's, I think, where we're going to be, 55. I want to sort of, okay, do.
Really quick question about that
Yeah,
formula. What is
sure,
big
go ahead.
N? What is big N?
Capital N is the number of data points in total across all of the groups.
And then you're subtracting from that the number of groups.
Yes.
Hmm.
And so rather than diving into the inner workings of the ANOVA procedure today, I want to jump gears into just highlighting the terms that we will be learning, okay? And then ultimately show you on that next slide what our book will call this word equation approach, which will be very helpful in the long run. Okay, so in chapter 1, and we're going to sort of in the next class session talk about the general linear model, and that will drift into chapters 2 and 3 as well. Tomorrow or next class session, we'll talk about partitioning variability via the ANOVA table. Okay, we'll use a geometric analogy, but I want to, before the lab today, focus on what our book terms a word equation. Okay, a word equation is just a way of saying what relates to what depends on what. Essentially, rather than using equations per se, our text takes this strategy of saying you just list off the explanatory variable or variables on the right hand side, and on the left hand side you tell me what depends on them. It's a way of emphasizing the concepts and focusing in on the things that matter the most. In our equation here, okay, I would say diet is on the right-hand side and lifespan on the left. So our word equation for this analysis here is lifespan equals diet. Now, when I say equals, I don't literally mean equals. How long you live is not equal to NP or N/N85. But if how long you live is a function of diet plus randomness, you'd say there's a dependency. So I actually don't love the equation here part, the equality, but I like to say depends on. The word equation is a way of saying what depends on what. The lifespan depends on what you eat. We're considering models of that sort. In the lab today, one of the things I'm asking you to do is to do an analysis of an experiment where we look at the job qualification scores as a function of what handicap a person has. In the earlier example, where we in chapter, well, the revision chapter with the t-test, we say the number of flowers depends on the sex of the tree. Okay, right hand side, it's what is, it is the explanation. The left hand side is what depends on what's on the right. So let's maybe clear that and see if there's anything I wanted to say before the lab. Okay, so I'm going to introduce the lab now by explaining the experiment, and then you'll go free on the lab. Hopefully it'll work well when we put you into groups. But any questions before I explain the data in the experiment? Any questions what we've done thus far? Okay. So in this experiment that you're going to be working with on discrimination against the handicapped, the goal of the experiment was to determine if individuals who have some handicaps are either favored or discriminated against in the hiring practice, okay, in the process of hiring. And so a group of graduate students at Ohio State in the College of Business there, and they all wanted to be HR people. So, you know, the folks that do the hiring in part, okay? They were shown a videotape of a person being interviewed for a job. And, some questions were asked of the candidate answered, more questions, more answers, etc. You get to watch the whole interview. It took 20 minutes. And then the graduate student who's a participant watching this videotape was asked to circle how well qualified was this candidate for the job. They had been given a job description of the requirements of the position, and then they saw all the answers that were given. And the questions were, what grades did you have in college? And, can you talk about this experience you had listed on your resume? And none of the job requirements were related to the person's handicap or displayed handicap in the videotape. The 4 separate handicaps that were shown were a person had an amputation in one of the videotapes, okay, an amputee. A hearing aid was displayed, so you presume the person has some loss of hearing. Crutches, they had crutches. They walk into the interview with crutches. And then in a wheelchair, they roll into the interview in that 4th handicapped position. No apparent handicap in the videotape was the 5th of the 5 separate job interview videotapes. You watch a videotape, you circle a number on the scale 0 to 10, and then you're done. Okay, so far so good? Some student will always say, hold on, what if the person with the crutches actually had really good grades in college and the person with a hearing aid had horrible grades in college? Could it be the grades that caused the difference in the job qualification perception of those watching the videotape? Could it be based on, college grades or work experience? Yeah. And so that's why it's a cool experiment. It's the same exact pair of actors reading the same exact scripted job interview. Everything was identical except for the actor playing the applicant in one scene had a wheelchair. In one scene had a hearing aid, which you could see in his ear. In one scene, there was no apparent handicap. In one scene, the arm was sort of taped behind the back. So it looked as though this person had an interview, amputation. Can I, shake your hand? No, I can't. I've got this amputation thing going on. So each student who was an HR candidate for an MBA program, sort of MBA program wanting to be in the hiring field in part, evaluates one videotape. They never got to know which other students saw which other videotapes. See, all you know is the one videotape you watched. And so I'm claiming either all the averages should be the same across all 5 groups, or if there is a difference between one group and another, it would probably be because of some sort of discrimination, because it's the same answers, same grades, same GPA, same work experience. Everything's the same except for the appearance of a handicap. Clever experiment, right? Catch the cheaters. That's what life's all about. Okay, so what I want to do is sort of stop sharing now and stop recording, so that way we can save this for later. And then I'm going to put you in your breakout groups. And if you're in one of the asynchronous groups, and I know there's a couple of you do show up for this live, but then do the work asynchronously later, that's okay. And